Evening. Thank you all for joining for today's session. So, those of you who are new today, let me briefly introduce myself. I'm Mo Chandra. I'm your TA for this course, and a brief introduction about myself. So, I am a PhD scholar at the Department of Chemical Engineering at IIT Kanpur. My thesis topic is in the area of tissue engineering and biomaterials, where I'm working in the field of 3D bioprinting. Other than that, I have worked with various kind of other techniques like electrospinning, freeze drying, etc. So these are the terms you must have heard by now when you are going through the lectures, right? So I have some experience in working in these techniques. And if you like to know more about my work, I feel free to explore my website. The link is given here. And if you have queries, you can ask me during the session or you can post in the discussion forum. All right. So like every Saturday, like the what we have doing for the last 2 weeks, we are going to meet from 4 to 6 p.m. The link is with you. The session is recorded and it is uploaded in my YouTube channel. Usually upload it by Sunday morning, so you guys can have a look afterwards. The notes is also uploaded along with it, and all the session are recorded, and also I note down the number of people who have joined and their respective name. So the attendance is basically recorded for each session, and I also supply this information to NPTEL people. All right. So and I also plan to take one revision session towards the end of this course, just before your exams. So if you have any queries that is not yet completely addressed during my sessions or through the lectures, feel free to, there is a session afterwards as well. So yeah, we can discuss more on it. So the platform that you have joined today is MS Team, and it does not allow you to access the chat option. So whatever queries you have to unmute yourself and then speak. Otherwise, you can also raise your hand so that I can call upon you and then you can speak. Else, if you have nothing to say, and then I request you to please mute yourself so that we don't get background noises during the session. All right. So before I start with the question, I forgot to put a slide on recap. So quickly, in words, I will recap. So for week 3, what we have seen, we have deeply studied few classes of biomaterials, and we also looked into few scaffold fabrication techniques, right? So previous week also we looked into biomaterials and why biomaterials are needed. Now we looked into a special class of biomaterials called hydrogels. So hydrogels are usually polymer. Natively, they are polymer, and they are in why some polymers are called hydrogels, because they have the unique property to absorb a lot amount of water and retain it. All right. And using this hydrogel, you can create different kind of scaffolds, and the techniques that I use already been discussed. Also, we discussed about ceramics or bioceramics. Why bioceramics? Because these ceramics are extensively used for biomedical applications, and for which type of ceramics are used, their examples, their properties, right? So mainly ceramics are used for orthopedic and dental applications, because that is the tissue whose ECM is most accurately captured by the ceramic, right? And for soft tissues, ceramics are not generally used. And we also looked into a new concept called self-assembly. Then we also briefly looked into what is 3D bioprinting, and how can you do 3D bioprinting, what are the techniques available, how would you make a bioink. So these are the things that you looked into week 3. So what I'll do today, I'll discuss few 20 questions, around 20 questions with you guys, which is related to the topics that you have studied in week 3. So I request your participation during the session. Don't make me answer all the questions. This session is for you. So I want you guys to actively participate in answering the questions. All right. So this is the first question that is in front of you. Which is not an application of hydrogen? replacement of bone, breast implants, conductive electrode coatings, drug delivery depot. For which of these applications you cannot use a hydrogel? That is the question. Anyone? So what are hydrogels? Anyone, what are hydrogels? Has anyone seen a hydrogel in their life? Like in a daily application, have they seen any hydrogel? Are you able to visualize what is a hydrogel? Anyone? Unmute yourself. The question is for you guys. So if anyone likes to eat jello kind of stuff, so that is made out of gelatin. So those kind of structures are actually hydrogel because like it can retain a lot amount of water and it needs cross linking, some kind of physical or chemical cross linking to hold the individual polymer chains together, right? And we get pores in between. That pores can hold a lot amount of water and it can swell and shrink accordingly. All right. If you dry it, then it will shrink. If you put it in a water environment, aqueous environment, then it will swell. So now if you're able to visualize how hydrogel will work or how it would look like, so for which of these applications you would not recommend to use a hydrogel? Come on, it's an easy question. Anyone like would like to give it a try? Are you guys able to see my screen and hear me properly? So there are 8 people who have joined, and is maybe my connectivity is an issue. Are you guys not able to hear me?
Hello, yeah, can you hear me now?
Okay, you
I
guys
don't
can hear
really,
me. Yeah,
yeah, I don't really think I can see the screen.
you can see the screen or not?
No, I don't think I can see the screen. I don't know if it's just my issue because I just joined right now, so I'm very unsure.
Okay, okay.
Yeah,
So
yeah, right now I can see it. No, it's not yet.
you
So yeah,
can you can see the screen? Yeah,
yeah, now I can see.
yeah. So I just want to know, like, are you guys able to get what the question means and what is the correct answer according to you? I'll give you a few more seconds. Yeah, go ahead if you want to answer.
No, I just joined right now, so I'm just kind of really confused.
Okay, you're confused? Okay, fine. That's fine. You should like interact so that I come to know.
Sure.
Yeah, it's great that you shared that you're not able to get. So is anyone else is able to get, like, okay, one person has said that he's not able to get, but what about others? I hope you guys have seen the lectures, right? No? Yes, no? Have you guys gone through the week 2 lectures or week 3 lectures? You have to tell me. Then only the discussion makes is
Okay, if
fruitful.
it is if no, if it is me, no, I haven't yet gone through lectures. Week 1, week 3.
week 3, you bit confused with the content. Okay, okay, that's good. Okay, that's fine. You're just learning, and it's a part of the process. So the correct answer for this question is actually bone. Like you cannot replace a bone just by using a hydrogen. Whereas why it is that? Because hydrogens are weak, mechanically weak. So if you guess that a lot amount of water is there, so the polymers which are inside the hydrogel network, they are not densely packed. All right. So water is taking up a lot of void space. So you can easily squeeze it. And that kind of mechanical property is not required when you are talking about bone. Bone is a very hard substrate. It is the load bearing organ of our body, right? So you cannot replace a bone using a hydrogel. Whereas hydrogels are very well explored for drug delivery, suppose. All right. They are making alginate beads into which they are loading some drug. And since hydrogels, as I can be easily squeezed, so you can inject those beads and it can squeeze through your blood vessels and reach the site. All right. So for drug delivery, it is very extensively used. Then the breast implants, which are made up of silicone. Silicone is actually a type of hydrogel. All right. Then there are also conductive polymers, and these conductive polymers are having a characteristic like an hydrogel. So when this the overall term could be conductive hydrogens. So conductive hydrogens can be used as a coating for sensors which are used for biological applications. So in those cases, when you want a soft substrate, right? You want a soft substrate, then hydrogel coating can give you desired property, like something soft that is not very rigid. So that kind of coating is possible when you do it with a hydrogen. Okay, so that is why the correct answer is replace. Like we cannot replace bone just by using a hydrogen. All right. Now this question is based on the topic of bioceramics. So what are ceramics? Ceramics are basically, if you want to visualize how the ceramics would look like, if you guys have seen a piece of chalk, right? So that piece of chalk, which is very nicely, packed into a cylindrical shape, that can be a visualization of ceramic, how a ceramic based scaffold would look like. It's like that. It's rigid, but at the same time, it is brittle. If you drop the chalk, it will quickly break, but it is rigid also. When you drag it on a hard surface, then it will not easily break. So in that way, ceramics work. All right. So depending on what to understand about ceramics, I want you guys to give it a try. So, what are the advantages of ceramics as a biomaterial? So, here you have to choose more than one option. More than one option is correct here. Bioceramics can accelerate osteogenesis. It then uh, compromise mechanical properties, applications in yeah, veteroblasty, then kinoplasty, and low fracture toughness. So when you are using ceramic, what advantages does it have? It is a question online based on that. The advantages of bioceramics.
Uh, okay, I think they okay, they're brittle. So what is vetroplastic? No, vetroplastic. What does that mean?
So
Is
these
it
two,
something to do with
yeah,
vertebrae and their replacements? Then
yeah, yeah. So you're actually in the correct track. So these are basically surgical techniques where they try to repair some spinal injury.
okay,
All right.
probably we can use bioceramics as well because bone material is also tough and
Yes.
brittle, and even the bio ceramics are also tough and brittle.
Yes.
And
Yes.
since it's ceramic kind of, I think I saw the next step. I think calcium phosphate is also a bioceramic, so acts rate osteogenesis.
Yes. Yes. That's
And
correct.
then
Yes,
Composite mechanics, it's a disadvantage and low fracture toughness. I don't understand the sentence.
okay. So low fracture toughness means okay. So you guys have not yet been taught, but let me just show you a graph. This is a stress versus strain graph. All right. For a ceramic kind of a material, what happens when you, so this stress or strain can be of tensile or compressive nature, either. All right. So when you apply stress, or say tensile stress, when you try to take a block of ceramic, you try to give outward force, you try to extend its length, that is tensile stress. When you try to do that, then what happens, you, it will quickly break. All right. So there is a region called linear region, that is called Hookean region, where the stress and strain are proportional. So it is also called elastic region. That elastic region for ceramics is very less, and then it quickly breaks. So that is the point where it breaks. So what is toughness? Toughness is defined as the area under this curve. The area under this curve is called toughness.
The area under the hook.
Area under this stress versus strain curve is called toughness. So ceramics, they can easily fracture. So it is not an advantage of ceramics. It's a disadvantage. That is why D is not correct here. Got it? So as I told you, ceramics are brittle, means if you increase stress after a certain level, it will easily break. So the toughness, they are not very tough. Whereas in metals, the toughness is very high. So you will come across this later on. Okay. So if you want to explore more about mechanical, this is taught under the mechanical properties of materials. All right. So that is a separate area, but very, you guys should know what is the mechanical properties, how you quantify it using stress and strain. When you talk about, when you study a course like biomaterials, where only materials are discussed, I can recommend you guys to do a course by Professor Mukesh Doble. The course is called Medical Biomaterials. All right, it is also floated in NPTEL. So there you will understand better about material properties, and then the term toughness or fracture. What is fracture? These things will become much more clear. Okay. So as you guys, you have already stated that A and C, you feeling like it's correct? You're correct. So these are correct answers. And ceramics mechanically, when you talk about mechanical properties, they are much more superior in comparison to polymers. All right. So yeah. So these two are correct option. So for others, is it clear? Only one is responding, so I'm guessing that others are also getting. But if it is otherwise, means if someone is not getting, please let me know. Is both the questions clear? You can react with a thumbs up, maybe, if you don't want to speak. That will help me understand what's going on here. Okay, I'll continue. Okay, so if you have any doubt, feel free to unmute yourself and ask. All right, for the sake of time, I'm continuing. This is the next question. Choose a scaffold fabrication technique that involves cell electrospinning. So you have seen a lecture on scaffold fabrication, right? And these are the names that you must have seen in that lecture. So I want you guys to tell me which of these techniques can be used to make cell-laden fibers. Here, cell electrospinning means you want to make some fibers into which cells can be embedded. I'll talk more about this method a bit later, but based on the name of this technique, try to guess what could be a correct method to get this kind of a architecture where you have a fiber and cells are embedded in it.
D. Option
Uh,
D, ma'am.
Option, can you repeat?
D. D. Fourth option.
Fourth. Okay. So, what about others? Do you guys also feel it is four?
Is it leaching method? Because the cells actually, I'm very unsure about the methods, but it's just like responding by the words like leaching, I think. But not sure.
I didn't get. Can you repeat? Maybe speak much more clearly. It will help me understand better. Can you repeat?
No, just by the the wording, I just feel it's leaching method because the cells are to be embedded, I guess. Unsure. I'm not sure because I haven't gone through that sessions.
Okay, okay, it's fine. So, um, I guess Sugatha correctly answered. The correct option is fiber spinning method. So, for those of you who don't understand what these techniques are and how the result is going to look like, so let me briefly explain. So, 3D printing is a technique where the material, say cell containing material or only biomaterial, it is deposited in a layer by layer fashion. So this is one layer, this is another layer, this is another layer. And how this deposition is done, there is a robotic arm like this, and it moves in X, Y, and Z direction. In this way, the material deposition is happening in a layer by layer fashion. Whereas in phase separation method, so this is a class of method. Under this, very commonly used technique comes that is called freeze drying. Here what we do, we first take a hydrogel sample, we freeze it at a very low temperature, like -80 degrees Celsius, and then we subject that material for drying at a very low vacuum and very low temperature. Then here what happens under low vacuum? So we apply low vacuum and low temperature. So under these conditions, we are manipulating the thermodynamic property of water. So we usually freeze dry hydrogels which contain lot amount of water. We subject the removal of water directly by sublimation. So here water is in ice form when it is freezed initially, and when we allow the water to be kept in a low vacuum and low temperature condition, then the water converts directly to vapors. So here what process is happening? Here sublimation is happening. Here the intermediate phase transition, that is through evaporation, is not taking place. Water is not converted to liquid and then it is not converted to vapors. We are directly converting water in ice form to vapors from the sublimation. So this is called phase separation. When we do this phase separation, what happens? So if there is a hydrogel block and there is like ice crystals, when it gets removed through sublimation, it leaves behind what? It leaves behind pores. So this is a technique to create a highly porous scaffold. And there is another method called leaching method. Here what happens? One classic example of leaching method is solvent casting and porogen leaching. So here what happens? You again prepare a solution. This is say a solution of polymer plus solvent, and you also add a porogen. Porogen means it is can be a NaCl salt crystals. Okay, NaCl salt, it can be NaCl salt crystals, and you mix it very nicely, and then you cast this particular solution into a mold. So what you have some salt crystals, NaCl salt crystals embedded in it. Then you cross-link it. Then what happens after cross-linking? The polymer with solvent, it forms physical or chemical bonds and it solidifies, leaving behind the NaCl in its intact place. Like whatever place it was there in the solution, it gets set there. Then after cross-linking, you dip that particular scaffold into a bath of water. Then water, what will do? It will dissolve out the NaCl crystals out of it. And when you remove from water, you will get a hydrogel block with pores inside. So these pores are basically the previous residents of NaCl crystals. So this is called leaching method, and I just explained one type of leaching method. It is called solvent casting and porogen leaching. Whereas in fiber spinning method, this is again a very classic example of this class is electrospinning. So I want to show you this particular diagram to explain what electrospinning is. So let me just remove it quickly. So here what is happening? We are we are loading some polymer solution here, all right, in this particular syringe. And this polymer solution like should be biocompatible, and you can load the cells as well in it. So this is called cell electrospinning. When you're using cells and polymer together, then the method is renamed as cell electrospinning. If you're not using cells, then it will be just called electrospinning. Here at the and this tip through which the polymer and the cells is going to be extruded out, it is made up of metal. So when we apply some current at this particular needle and the surface onto which the fiber is going to be accumulated. So these two places, they are oppositely charged. It can be positive charge and it can be negative charge. Or it is also possible that the plate is grounded. Okay, it means it is connected to ground. Both ways is possible. You either keep it opposite charges or you place the plate in a ground state. So when you are applying electric field and you're also applying manually force through a syringe pump to extrude out the polymer solution with cells, then the polymer which is coming out, that a drop comes out, suppose that drop gets temporarily charged. It gains some surface charge onto it. And since oppositely charged surface is there, just perpendicular to it, then what happens? That charge pulls it, that it pulls the polymer, all right, in its direction. So in that way, it is like basically drawing out a drop of polymer solution into fibers. And when that happens, and you're then we get fibers that is collected onto this plate, and the fibers can look something like this. Now, if you have cells also, so polymer along with cells will get drawn out, and the cells, it can be embedded inside the polymer, or the if the cell size is large and if the fibers are of smaller dimension, means smaller than the size of the cells, then the cells can also can like just sit over the fibers. So in this way, the morphology of the fibers, how it will look like, the alignment of the cells, these things have to be optimized. All right. You have to play around with the voltage that you are going to use, the viscosity of the polymer solution that you have used, then what kind of the distance between the needle and the plate, that is also have to be optimized. Because if keep the plate at a very close distance, then what will happen? You will get very thick fibers. All right, and it can also happen that they merge. So here solidification is happening just by evaporation of the solvent. So solvent are usually organic solvents that people use to dissolve the polymer. So they are just evaporated. So when it is evaporated out, the polymer solidifies and forms the fiber. There is no cross-linking that is happening. It is just solidification in presence of air. You can chemically cross-link it by in presence of some chemical that is post after you have electrospin. So many things have to be optimized here in order to get desired results. So I hope I could like briefly explain what all these techniques are. And if you have any queries, let me know. Are there any queries from anyone? Okay. So I'll assume that you're able to, you have got little bit, if, but I request you to go through the lectures on your own once so that the concept becomes much more clearer in your mind. You can visualize the process. All right. Now, regarding 3D printing, what do you think this technique is? Is it a top-down approach or a bottom-up approach? So what is top-down and what is bottom-up? So top-down means you are creating the like the largest component of a tissue. That is, you are first creating the scaffold that is mimicking the ECM here. All right. And then after creating the scaffold, you are seeding cells. The cells are the smallest component, right? So first you prepare the scaffold and then you seed cells. Whereas bottom up approach, what happens? You first create cells plus some material, biomaterial, the smallest block, maybe in form of a sphere or in form of a fiber, all right? Or and then you assemble these spheres or fibers into a larger 3D structure. So these spheres, they can be packed like this. If there are fibers, then they can be stacked over one over other, right? To create a 3D structure. So that is called bottom-up approach. And this is top-down. You start with the largest component and then you slowly move towards the smallest component. Where bottom-up approach, you first make the building block of this 3D structure. Here, cells plus biomaterial like a sphere or a filament, and then you assemble it to create a 3D structure like a scaffold. So now if you have understood what is top-down and bottom-up, where 3D printing lies? Does it lie here or here? Where does 3D printing lies? The previous slide, I told you what is 3D printing. Here we do layer by layer deposition of materials, right? So just equate these two things, layer by layer, and whether it is top down or bottom up. See, even if you have not seen the lectures, you can give it a try, just listen to what I'm trying to say. And if you have any queries, ask me so that things become easier for you. You don't have to do too much self-study afterwards. Things become much more easier during these sessions and you can solve the assignments quickly. That's the point of doing the session. So that's why I want you to, give it a try, participate. Will boost your confidence. So session is not for me. Remember that. It is for you guys. Please take maximum advantage of these sessions. So 3D printing is top down or bottom up? Under which type would you place it? 3D printing is bottom up, right? Why it is bottom up? Because here first we are uh, making one layer, or you can say we are depositing one filament. If it is extrusion type of 3D printing, we are depositing one filament, then another filament like this, then another filament, and then we can create a second layer like this, then again a third layer like this. So when you repeat this over multiple layers, what you get? You get a block, you get a 3D structure. All right. So that is why it is called bottom up. So I've just shown you the example of extrusion where you are extruding a filament. You can also assemble drops. So you in inkjet 3D printing, they extrude droplets, and these droplets are assembled. So that is also a bottom up approach. All right. Is it clear? Is it clear to everyone?
Yes, ma'am.
Yeah, great. So others also respond, okay? Only two people are responding. That's not a good sign, right? If you are not understanding, please let me know. Okay. So this is the next question. Which parameter is used to define the mesh size of hydrogels? So I told you what are hydrogels. Hydrogels are basically polymer based, and there we provide some cross-linking, either physical type or chemical cross-links that links the polymer chains and creates a interconnected network structure. So as a result of cross-links, what happens? Some pores or meshes get created. Okay. So if you were to ask, how would you define the mesh size? Means then which of these option is best to define it? Whether you will determine the polymer volume fraction in a swollen state, average molecular weight between crosslinks, or measure the distance between the crosslinks. Logically, if say this is your one polymer chain, another the 3-4 polymer chains are there, and through some side groups, the crosslinks are formed. Okay, these are actually continuous. Some crosslinks are formed. When this kind of structure gets formed, it's a network structure. 3D network structure gets formed. This is 2D representation of how a hydrogen structure looks like. And what are mesh here? This is your mesh. So if I were to ask, what is the size of this mesh? What would you use to determine the size? From the figure, if you have understood the figure, tell me what would be the answer then. So these are crosslinks. Okay.
Ma'am, is it B?
Is it B? Okay, fine. So yes, you were
I'm not
saying
sure,
you're
but
not sure. Okay,
yeah.
okay, it's fine. It's fine. It's fine. It's totally fine. At least you should try. That's the main point. You should try. So the correct answer here is actually C. Why C? Because as I'm trying to show in this figure, mesh is basically the gaps or the void spaces that are left behind when the adjacent polymer chains are linked. All right. So those are the void spaces, or you can also call it pores. So in order to theoretically quantify the size of the pores, you have to know what is the distance between the adjacent polymers. And how would you know that? You would have to measure the uh, distance or the length of crosslinks. You can say the lengths of the crosslinks or the distance between the polymer chains. If you are able to do that throughout the 3D structure, then you can get a approximate size of a mesh. Okay, or you can if you can just get the distance between in 3D space. Uh, so if this is the crosslink in the paper and there is another crosslink that is out of the paper, then in 3D space also you can get a distance between these two crosslinks, and then you can get a approximate size of how the mesh would look like. Now, why A and B are not correct here? The polymer volume fraction, it tells us about how much the polymer content is there. So hydrogel is made up of two things, right? Water and polymer. We quantify the water by saying what is the salt fraction or solution fraction, and polymer by saying the polymer fraction, or it is also called gel fraction. This quantification helps us to understand degree of swelling. Like indirectly, if the water content is high in the hydrogen, means it has swollen up a lot. Okay, so that will, so that's why option A is not correct here. Whereas option B, it helps you to understand the density of crosslinks. So what happens if the average molecular weight is high in the hydrogen? Means more and more polymer chains are there with some side groups, and so those side groups, they have the ability to form more crosslinks. So when you try to quantify how much crosslink is there in a particular volume or in a particular mass of hydrogen, then a good approximation can come when you know the average molecular weight, okay, of the polymer. So here the average molecular weight of polymer that is forming the crosslink. That is what that statement means. All right. Is it clear? Is it clear? Okay. I'll move on. But if you have any queries, just let me know. So which of the following can be used as a nano carrier? So nano carriers, you guys must have seen the scaffold fabrication techniques where they were making beads and all micro size, nano size carriers, basically some spherical particles which are of nano scale. So when you fabricate it, you can create various kind of nano carriers made up of different materials. So here are some options. You just have to tell me which of these options can act as a nano carrier. Liposomes, micelles, dendrimers, microcapsules, all of the above. Basically, a carrier, a vehicle.
May I answer? Fine.
Yeah. Go ahead.
Yeah, so I just got disconnected as well again. Liposomes are, dendrimers are, I'm sure about microcapsules and micelles. I haven't seen. Micelles also, I think. Yeah. So is it all of the above? Because I don't know
Yes.
about microcapsules. Okay.
Yes. So as the term say, capsules, like something, a cap,
Okay, something that can carry. Okay,
yeah, okay.
nice.
So yeah, so you're correct. It is all of the above. So if you like to know more about how liposomes are made and how micelles are made, I may not be the right person because I've not worked a lot in this area. But yeah, you can Google it. You can find the structures. In brief, I can say that liposomes are made up of lipid particles, just like our lipid bilayer. So it similarly they try to match it where hydrophobic group is inside the core towards the core and the hydrophilic group is on the surface. So it creates a self-assembled lipid structure and within the hydrophobic core you encapsulate some drug. Okay, where micelles it's just like the soap can form micelles, right? So just like that they use detergent to make that micelles. I'm not sure about how the dendrimers are made, but microcapsules I can tell you, like similar to alginate beads, you take some alginate solution, all right, and you pipette it out through a small aperture, all right? You extrude it through a small aperture into a calcium chloride solution. And what will happen? The drop of alginate solution that is coming out, it's going to immediately cross-link and form a bead kind of a thing. So if you are mixing your sorry, if you're mixing your alginate solution with some drug, then what will happen? Within the bead, you will have some drug. So that is a kind of a capsule thing. Okay, looks like a capsule, but there are other techniques to make it. But all of these are carriers or form of a carrier. The property will change, and which one to use, it depends on your application, what you want to load, what is the charge, how fast it can degrade, and all those properties you need to look first in order to choose which nano carrier to use or micro carrier to use. Okay, then self-assembled based colloidal structures based out of or composed of lipid bilayers. They are called. I just previously told you.
Like
So liposomes, yes. Right. So I'll not go into detail, but it is related to that question only. Okay. Now state which of the following statements are true or false about hydrogels. First, I'm reading the first one. You have to tell me whether it is true or false. Hydrogels are insoluble due to the presence of crosslinks. Is it true or false?
True.
Yes. Then hydrogels are mechanically rigid. Is it true or false?
false.
False. Ceramic-based hydrogels also exist.
True.
True? Are you sure?
So I have read some papers. So like a composite they have been using along with the polymer.
Yes. Composite form hydrogels are there, but only ceramic-based hydrogels are not there. Means they mix a hydrogel polymer with ceramic, like you can mix collagen. Collagen is a hydrogel, you mix some hydroxyapatite particles in it and then cross-link it. But what happens in the 3D structure? You have hydroxyapatite particles floating around. Okay, so that kind of composite hydrogel exists, but only the backbone is ceramic or like it cannot exist, means it is not yet reported. Only where ceramic is having the capability to retain a large amount of water, only a polymer based hydrogels exist. All right, that's why it's false. Composite hydrogels with ceramics with nanoparticles and those do exist, people have reported it. Okay, we're not talking about the composites here. Okay, now, the fourth one, in IPN hydrogels, interpenetrating network hydrogels, two hydrogels are covalently linked. Is it true or false? So, what are IPN hydrogels or interpenetrating network hydrogels? Anyone recall it through lectures, maybe? So IPN hydrogels are basically made up of two hydrogels. First hydrogen network is formed, all right, through cross-linking. And next component is basically added on top of it in a solution form and then cross-link. So this is the first one. You add hydrogen solution of this a solution of the second hydrogen on top of it. Then what happens? You get a this first one and this is like second one. So in this way, the polymer chains of the first and the second hydrogen, they kind of intertwine like with each other. So in this way, IPN hydrogels are formed. Okay. Now, what kind of interaction goes on? Is it covalent interaction or non-covalent interaction that holds these two hydrogens together? Actually, it's non-covalent. Okay. Some hydrogen bonding or electrostatic interaction, like these forces plays an important role in uh, to holding these two hydrogens together. But individually, the hydrogens can be covalently bond. Like first hydrogen can be covalently bond, and then second hydrogen can be also done. But together, they might be non-covalent interaction. Okay. So that is how IPN hydrogels are made. So what then? The correct answer is false here. Okay. Is it fine? Yeah. Now, this is the next question. Which of the following fabrication techniques comes under additive manufacturing? So what is additive manufacturing? Anyone like have read anywhere? So additive manufacturing means when you are adding material on top of one another. That is called additive manufacturing. There is another term called that is called subtractive manufacturing. Here what we do, we take a block of material and remove the unwanted material in order to get a 3D structure. That is called subtractive. You like sculpting ho gaya is an example. Sculpting, you sculpt out, right? You take a piece of rock and the artist, it removes the excess amount that is not required so that it can create the desired 3D structure. But additive manufacturing, you add small amount of material on one another. That is called additive manufacturing. So based on what I've understood about electrospinning, 3D printing or 3D bioprinting, gas forming, particle aggregated scaffold, which of the following techniques will come under additive manufacturing? Yeah, that's correct. So with 3D bioprinting is the correct one. Here, gas forming is completely different. Here you take a block of hydrogen within which there is some gas evoluting agent. Okay, for example, ammonium carbonate, which in presence of an aqueous environment, it effervesces, all right, and releases carbon dioxide gas. So that gas, when tries to comes out from the block of the hydrogen, it leaves behind empty spaces. So that is how you can create a porous hydrogel scaffold using the gas forming technique. Here, particle aggregated scaffold, here what we do, we individually first make the particles, all right, maybe micron size or nano size, and try to aggregate it. Means we try to compress these particles together, and if some covalent and non-covalent bonds can be created between these particles so that they stay connected to each other. So it's like making like you take a small piece of mud and try to clump it. Similarly, you take a large amount of particles, put it in a mold and press it. Okay, and in presence of some linker, you try to cross-link it so that the particles stay together. So that is called particle aggregators. And in this way, you can create a 3D structure, and that is the scaffold. So this is 3D bioprinting is the correct one here. So this question is directly from the lectures. So those of you who have seen the lectures, try to answer. Others, just it's just a textbook question. Okay, already discussed in the lecture, nothing extra to add here. So what is the component of original bioglass? So bioglass is a type of bioceramic. Okay, and what was the composition of the bioglass that was first made? What it contained of? So bioglass, let me give you a hint. It is made up of those elements that are naturally found in our body. Okay, like calcium, sodium, phosphate, oxygen. Okay, so these are naturally found in our body. So that, and people try to make it using these elements so that it is much more biocompatible. It can be easily accepted by our body without giving some adverse effects. So now you try to guess um, which is correct here. Others who have seen the lectures, you must try to attempt and give me the correct answer. A, B, and C. I'll give you a few seconds to think over and answer.
A.
Option A. Okay. Can I expect one more response if anyone would like to try?
A.
Okay. So the correct option is A. So if you go back to your lectures, their professor has discussed the composition of the original bioglass. It consists of 45% silica, okay, SiO2, 24.5% calcium oxide, 24.5% sodium oxide, and 6% phosphate oxide. Okay, so this is the composition of the bioglass. Now, another question. Physically cross-linked hydrogels, they can be reverted back to solution state upon changing the polymer configuration. Is it true or false? So, true. Okay. So, you're correct. So, if the crosslinks are weak, means maybe it is made up of some ionic crosslinks. So, if you remove those ions, then the solution, it can revert back to solution state. Similarly, if the physical crosslink is due to crystallization, if you heat it up and then it will heat it above its glass transition temperature, then the crystalline nature will be compromised and will turn back to amorphous nature or to completely solution state. Also, if you like configuration means many polymers, they have random structures in the beginning. Some physical cross-linking agent is added or stimulus is given, because of which the polymer configuration change and some physical bonds create. So in this way, if you remove that stimulus, if you maybe like heat it up, then the hydrogen bonds can break and it will revert back to solution state. So physical cross-linking, as the term suggests, is not permanent. It is irreversible in nature. That is what I wanted to make you remind. So that is why also physical cross-linked hydrogels are mechanically less stable when we talk about chemically cross-linked hydrogels. If you do degradation kinetics, where we study how fast the hydrogel is degrading, means slowly losing its 3D structure, then physically cross-linked hydrogels will have a faster degradation rate when you compare it with chemically cross-linked hydrogels. Okay. This is next question. Shrinking effect due to phase transition happens on thermoresponsive hydrogens. At what temperatures? So there is a class of smart hydrogens that is called thermoresponsive hydrogens, where in presence of particular temperature range, it can swell or shrink. Okay, so hydrogens can either have a lower critical solution temperature or a upper critical solution temperature. So those of you who have seen the lectures, try to answer first, then I'll explain. Okay. Okay. I guess you're not able to understand. So the correct answer here is this option D. Now let me come to explanation part. So the hydrogens which have a upper critical solution temperature, these hydrogens they exhibit swelling, okay, swelling and shrink. It can they can swell when the temperature is below this upper critical solution temperature, and it can shrink when the sorry, I was correct. Yeah, sorry. I was saying that hydrogens which exhibit upper critical solution temperature, they can shrink at temperatures below this. And if the temperature is higher than upper critical solution temperature, then it will swell. Whereas it is opposite for those hydrogens which exhibit lower critical solution temperature. So here they will swell when the temperature is less than lower critical solution temperature, and they will shrink when it is greater than lower critical solution temperature. A very good example of thermoresponsive hydrogen is Panipa. Okay, the full form is very long, that's why I don't remember, but in short, it is called Panipa. So it has a lower critical solution temperature of 32 degrees Celsius. So very close to physiological temperature. All right. So when we expose this hydrogel solution of 32 degrees Celsius or greater than 32 degrees Celsius, then what happens? Temperature greater than 32 degrees Celsius, then the hydrogel swells. So it becomes, if it is a bead form, so the bead becomes larger in size. Whereas if the temperature is lower than that, means then what happens? Sorry, my mistake. Since it exhibits a lower critical solution temperature, when the temperature 32 degrees Celsius, that is the low critical solution temperature. When the temperature is above greater than 30 degrees Celsius, then it shrinks. Sorry. Then shrinking happens. Means if whatever drug or you have loaded inside the hydrogel, they will not get released. It will shrink. Okay. The network of the hydrogel, they will try to condense. Okay. Whereas the temperature is when the its supplied temperature, say at room temperature, when you place the hydrogel at room temperature, which is much lower than 30 degrees Celsius, then what will happen? It will swell. Then the polymer chains, they will try to come out, like expand, because water can get in, and whatever drug you have loaded inside, they will easily come out. So this kind of stimuli like temperature, pH, etc., are very useful when you are trying to do controlled drug release kind of applications. So these kind of polymers which respond to this stimuli like temperature are very useful. And only to control the drug release, you just have to control the temperature. So if you keep it at 30 degrees Celsius or 37 degrees Celsius, usually like inside the body, then you can expect there will be no drug release. Okay. But when it is come out, then the drug release will be there. So this is one example. Similarly, there are other examples of this kind of hydrogels that you guys can look up. So is there any doubt here? Just quickly go through the lecture, go through the slide, read it once. You still have doubt, let me know. Again, let me repeat. The hydrogels which exhibit LCST, they have a tendency to swell when the temperature is less than, okay, when the temperature is less than LCST temperature. Whereas it will shrink when the temperature is above its LCST temperature. Whereas the other class of hydrogens which have upper critical solution temperature or UCST, they will swell when the temperature is higher than UCST, whereas they will shrink when the temperature is lower than UCST. So through modulating the swelling and shrinking behavior of a hydrogen, you can modulate the release kinetics, either of drug, growth factors, or any other component that you wanted to deliver, you can do that. Usually drugs and growth factors are delivered through this strategy. Is it clear? Is it clear?
Yes, ma'am.
Yeah. This is the next question. Which of the following factor does not, okay, does not influence the diffusion of solute through the pores of hydrogels? Pore size or mesh size, solute size, hydrogel viscosity, temperature. It will not influence. So the following factor will not influence the diffusion of solute. So as I am repeatedly saying, hydrogel is basically a network of polymers, all right, where the crosslinks are there to hold the adjacent polymer chains together. So it creates a network or interconnected network structure where the pores are there. So if any transport of supposed to happen, then transport through the network, it is going to happen through diffusion. Okay, so diffusion, I hope you guys understand what happens. It is the passive movement where there is no requirement of energy, and the driving force is only the concentration gradient. The solute moves from a region of high concentration to low concentration. That is diffusion. So if the solute has to diffuse through the network or through the pores of the hydrogen, then what will help and what factor will not help in it? So you have to tell me what factor will not play a role or will not at all affect the diffusion of the solute through the hydrogen. Is it the pore size, the size of the solute particle, viscosity of the hydrogen, or temperature? Please note the solvent here is the water, obviously. Okay. If you are or aqueous based solvent like PBS, means an aqueous environment we're talking about. Okay, the solvent. So what seems like the right answer here? Does the pore size have anything to do with how fast the solute can diffuse through the network? Yes or no? If the pore is very small, smaller than the solute particle, can it diffuse through it? Can the sol? Huh? Yes. Someone has unmuted. No, right?
Yeah.
Yeah. So if the pore size is very small, smaller than the size of the solute, then it cannot diffuse. Similarly, if the solute size is larger than the given pore size, then also it cannot diffuse. So A and B does influence the diffusion process. What about C? What do you understand by viscosity? Can a hydrogel have a viscosity, or when viscosity term is important? Okay, if you're not getting C, what about temperature? Can temperature play a role in diffusion? Can it affect the gradient, concentration gradient of solute?
It
Or
does
maybe
affect the rate, right? It does affect the rate, right?
can you repeat? Can you repeat?
It does affect the rate of diffusion, right?
Yes, it
Temperature.
can. Yes, it
Yeah.
can affect the rate of diffusion. So, if you increase the temperature, usually the kinetic energy of the solid particles it can increase. So, if the size of the solute and the pore size matches, then if you increase the temperature, then solute will have a much more higher tendency, like much more kinetic energy to pass through the pores. So B, A, B, D, all these three factors affect the diffusion process. So what does not affect is C, hydrogen viscosity. So why it is that, let me explain. So when we talk about viscosity or the term viscosity, it usually comes something like liquid comes to our mind, right? Something that can flow. So when we are talking about diffusion and pores and all, imagine that the hydrogel is not in liquid state anymore. It's in solid state. The crosslinks that has formed between the polymers that restricts the further flow of individual polymer chains. So before it formed the hydrogel, the viscosity was important. After the hydrogel is formed, the viscosity is not relevant here because in this case it's a solid. It will have an infinite viscosity. Think about it, right? you cannot quantify the viscosity. A solid material will have an infinite viscosity because there is a very high resistance to flow. All right. That is why C cannot affect the diffusion process when it is in hydrogel state. Is it clear? Okay. So moving on, this is the next question. You have to match column A with column B. So column A has the smart hydrogels, a list of smart hydrogels, and you have to match the relevant stimuli, environmental stimuli that can affect its swelling behavior. So anyone who would like to give it a try, take few seconds and then you can answer. Yes, go ahead. Don't be shy. Yeah.
Yeah, thermal responsive to temperature, cationic hydrogels, probably pH, because also depends on the number of ions, right? And then polyelectrolyte, electrolytes, electrical signals.
Okay. So yes, you're correct. Um, yes. This is what you said?
Yep.
Yeah. So you're correct. And like anyone have any query? It's straight from the lectures. Also, the name of the hydrogel itself gives you a clue what could be the electric stimuli here. We'll come to we have already discussed the thermoresponsive hydrogels, where the upper critical solution temperature and lower critical solution temperature, it does affect the swelling behavior. We have already discussed that in one question. I'll come to the cationic hydrogels and anionic hydrogels later on. Whereas polyelectrolyte hydrogels are basically like charge-based hydrogels, which in presence of an electric field, you can modulate the basically surface charge of the individual polymer chains and accordingly modulate its swelling behavior. Okay. I'll come to cationic or anionic hydrogels a bit later. I have a question ready for it. So anyone else have any doubt in this question? Okay, I'll assume that you have understood. Now, here's the next question. Insulin is released from glucose responsive hydrogels when glucose concentration is blank. Is it when it is high or low? A or B? The glucose responsive hydrogels are a special class of hydrogels which whose swelling behavior can change in presence of glucose. And insulin is encapsulated within this hydrogel. I'll explain in detail the mechanism, but from
It's going to be high because that's an insulin reduce. Yeah, insulin reduces glucose levels, right? So yeah, so whenever it's high, it kind of releases insulin as well.
yes. So if you think logically also, in our body, what happens when glucose concentration is high, insulin is released. Here opposite, we are increasing. If suppose in the environment the glucose concentration is high, the hydrogel is designed in such a way that it can release a large amount of insulin. Okay, so this answer is high. So let me explain quickly how this does this work, how this hydrogel is designed. Okay, quickly let me just explain. So there is a pH responsive hydrogel onto which you are immobilizing an enzyme called glucose oxidase or GO. Now, this enzyme can catalyze the conversion of glucose to gluconic acid. So, in presence of this enzyme, gluconic acid is formed. And the hydrogel, this yellow matrix, is a pH responsive hydrogel. Now, when surrounding environment has a high amount of glucose, so these are glucose molecules. If it is concentration is high, then the through the pores, the glucose enters the hydrogel matrix, reacts with GO enzyme or glucose oxidase, and inside the hydrogel, gluconic acid is secreted, right? Means glucose is converted to gluconic acid inside the hydrogel, because of which the pH inside the hydrogel drops. It becomes acidic. As I told you, the hydrogel backbone is pH responsive. So in presence of an acidic environment, the hydrogel swells. And as it swells, the insulin which was there, it gets released. If it is other way, if the glucose concentration is low, then the gluconic acid concentration which is going to be made inside the hydrogel is less. So the pH increment means pH will not transition towards acidic. So it will not swell and thus insulin won't be released. This is like in very basic thing I tried to explain how these glucose responsive hydrogels work in order to release insulin in environment where glucose concentration is high. Is it clear? I'll
So does the
yeah.
outer layer act like a diffusion barrier?
So diffusion barrier would be there, okay. But it's possible that the shrunken stage, like if suppose this stage is shrunken and this is swollen stage, still some pores will be available. Even if it is shrinked, the pores will be available. But we for the diffusion of the glucose, we want the pores to be sufficiently large that glucose molecules can go. And glucose are very tiny molecules, okay, very tiny molecules. They can diffuse through solvents like very easily. So that's why glucose is able to reach only, not any other component we're talking about, even in the shrunken stage. And insulin, which is of larger size, larger than the pore size in the shrunken state, it cannot come out. It needs that stimulus for pH to change in order to come out. Is it clear? Does it make sense?
It does, it does, it does.
Yeah. Now, this is the question about cationic and anionic hydrogels. So these two hydrogels belong to the class of pH responsive hydrogels. Okay. So based on, so you have to fill either acidic or basic. Only these two answers are possible here. So don't go thinking about anything else here. So you have to fill in the blanks either acidic or basic. Cationic hydrogels means they are positively charged. Their polymer chains are positively charged. Anionic hydrogels means they are negatively charged. So what will happen if you place a cationic hydrogel, whether it will swell or shrink in acidic or basic? That is the question. Okay. So first,
Was the glucose one a cationic or anionic hydrogel?
this one.
Yeah.
So it will be clear when we do this question. All right. You will only able to answer it if you are able to understand this question. Okay. Just hold that thought for a second. Okay. Let me just explain this question. Then you will be able to answer which type of hydrogel is used, cationic or anionic. So as I was saying that cationic hydrogels, it will swell in blank, acidic, or basic solution, while shrinks in blank. In blank, you can either fill acidic or basic solution. So acidic means there is a large amount of hydrogen atoms, right? That is why pH turns to acidic. And when there is basic, means OH groups are very high in solution. That is why the pH turns to basic. Towards after 7, the pH starts increasing. So here, first blank, the one that is I'm highlighting right now, here what will fit best, acidic or basic?
Can I ask one doubt? No, can you hear me?
Yeah. Can you repeat?
Yeah, so just one doubt. Does
Yeah,
the cationic or anionic hydrogens, do they compress or shrink because of electrostatic forces? Or yeah, I just wanted to know that.
so here electrostatic forces are not playing a role here.
I'm not playing
Here
it.
they are not playing. Here ions. What type of ions are present in the solvent? That will that is why the pH is changing, right? So
Oh,
based
okay,
on
it's an ionic component.
so uh, based on the ion and how those ions are interacting with the positively charged or negatively charged polymer chains, based on that, the swelling or shrinking will happen.
So I just think so probably cationic hydrogens has like a more positive charge. So then if the medium is like basic, then there's an affinity for positive charge. So I think the H plus or whatever proton's positive charge is going to move out and it's going to shrink. Just a guess, I'm not sure.
Okay. So you are saying for the first one, just I'm repeating what you said. Cationic hydrogens will have a tendency to swell in a basic solution.
No. In a it'll shrink in a basic solution is what I thought.
Okay. It will shrink in basic solution, but it will swell in a acidic solution. So what about the second one? I'm not saying it is correct or incorrect. What about the second one? Does this logic apply in second one as well?
I think so. I'm not sure.
So according to your logic, anionic hydrogens should swell in a basic solution, right? Well, it should shrink in acidic solution. Okay.
No, but then my logic and the vice versa can also happen. Even the OH minus molecules can also rush inside. So I'm unsure.
Okay, it's fine. It's totally fine. You just gave a guess. It's totally fine. Yeah. So you're actually correct in that sense. So what happens is when the positively charged uh, hydrogen atoms rushes in, then charge repulsion will happen inside the pores. So that is why it will have a like polymer chains are repelling from each other. So you get
So yeah, so
the overall.
electrostatic forces do play a big role over that, right? I think
Yeah, means
somewhat.
yeah, somewhat.
This
Yeah,
was the logic that I wanted. That is why
yeah.
I asked the question.
Yeah, means I was thinking you were saying maybe electric field was, but yeah, you can say wherever the opposite charge is there, some charge forces will be there. But that is the logic that is being applied here. Okay. Uh, so you are correct in that sense. So when positively charged hydrogen atoms they rushes in within the pores of the cationic hydrogels, they will cause repulsion between the polymer chains, because of which they have a tendency to swell. Whereas in the basic solution, their electrons, means, ions will try to, due to presence of basic solution, some attractive forces will be there, right? So it will shrink. Same is for anionic hydrogens. So coming to your previous question, here you asked for glucose responsive hydrogels, when we are using pH responsive hydrogels as a in the design, then what it would be, whether it should be cationic or anionic.
So we rely on
Anionic, yes. No, should be cationic, right?
oh yeah, okay, sorry.
Your swelling is happening because there is an decrease in pH, right? Decrease in
I
pH is,
just thought it was tricky.
yes, yes, there's no problem. So you will, for that application, people are using cationic hydrogels because acidic pH is coming due to release of gluconic acid, and cationic hydrogens, as I told you, have a tendency to swell in acidic condition, so it will swell and release the insulin. All right. So this is the next question. Choose which of the following ceramics are osteoconductive in nature. So osteoconductive means the biomaterial can allow uh, ingrowth, ingrowth of bone through it. Means bone can grow through the biomaterial. That is called osteoconductive. So based on the lecture of bioceramics, I have prepared this question. It's again very straightforward. Yeah.
So alumina and zirconia are like bioinert, so no include.
So these are not. You're saying these are not.
These are
Okay.
not. And, hydroxyapatite is just like bone composition, somewhat very close. Then I think rest of them do promote osteogenesis. Yeah.
Yeah. Okay. So the correct answer here is actually all rest of the four components. Okay. Here, the key concept that I want to highlight is all these four biomaterials, the coral apatite, hydroxyapatite, bioglass, calcium sulfate or POP. So they are all containing the ions or the compounds that is naturally there in our bone, right? So they are very much biocompatible for bone tissue engineering. They are naturally having the calcium ions or the phosphate ions in them. So the general observation that I had is any material which whose composition is much more similar to our native tissue, like in this case bone, it will show all the properties like osteoconductive or osteogenesis or osteoinductive. Okay, so all these properties are there. But people have reported that alumina and zirconia, they are not osteoconductive, but they are all osteogenesis means it will allow more and more formation of bone cells like osteoblast, osteocytes, etc. Okay, bone cells will happen, but deposition, the mineral component of the bone and further penetration of the biomaterial is not possible through these two biomaterials. Just it is this question is directly prepared from the lectures, that is bioceramics lecture I've prepared. Just quickly go through it, see the characteristics of each of these biomaterial, and you will come to know. All right, it will be much more clear. So the next question, which of the following is a driving force? You have a doubt? Go ahead.
Yeah, it was not regarding this question, it was regarding the glucose, the insulin, the hydrogen which releases insulin. So, do the molecules of glucose go like to the inside hydrogen because of the concentration gradient, or is it something else?
Change of concentration gradient, diffusion, through diffusion, yeah.
Yep. So, what about other molecules which are like very similar to glucose?
Yeah, yeah.
Will they also other molecules which have a similar size as glucose? Will they also stimulate the same response, or like?
So to test this, you can create a control experiment, okay, where there's a solution containing glucose only, and you create another solution where there is glucose and fructose, suppose, right? And you like dip the glucose responsive hydrogen in both. Now, in the first case, glucose will penetrate. Now, fructose, which is also having similar size like glucose, there might be some competition happening between these two molecules. As the entry spaces are limited and you are dipping it in a bath where equal concentration is there, so these molecules will try to compete, I think, okay, in order to get entry. So in the second case, it's possible that due to presence of fructose, the insulin release is less because the fructose will also try to go into, right? And only and glucose oxidase can only react with glucose, not with fructose. So pH change will be relatively less. Like a transition to acidic will be relatively less. That is why insulin release will be less in comparison to the first case. Okay. So if you think in that way, it can enter more molecules which are of similar size. It can enter, but there will be some competition, and ultimately the release of insulin will be affected.
Yeah, so there will be a decrease in efficiency.
Yeah, yeah. So yes, we were in this question. The question states, which of the following is the driving force for DNA double helix self-assembly? Hydrogen bond, dipole-dipole interaction, hydrophobic effect, covalent interaction.
By self-assembly. Okay. Generally, DNA double helix stays safe, like this of its bonding. What is self-assembly?
Yeah, yeah, yeah. So self-assembly is a spontaneous process, first of all, means uh, the assembling, as you understand the term, right? Assembly means some particles, they are trying to come together and assemble into something. So this process is spontaneous. First of all, you do not need to give any external driving force or energy for it to happen. So this process can happen in under equilibrium condition spontaneously on its own. That is called self-assembly. So if suppose and self-assembly is naturally seen in our body for DNA structure, protein folding is happens through self-assembly. Then formation of lipid bilayer, that is happens through self-assembly. So, but when this what so in these cases, these molecules, individual molecules which are there, they have to interact with each other, right? So usually non-covalent bonds are formed between these molecules that holds these molecules with one another, and we get a higher dimensional structure. So that is self-assembly, and the driving force is usually non-covalent bonds. So I've already told you that D is not the answer here. So now you try to,
hydrogen bond.
yeah,
Hydrogen.
hydrogen. Yeah,
Okay.
it's hydrogen bond. So similarly in proteins, there can be hydrogen bonding, hydrophobic bonding as well. So protein has different layers like primary structure, secondary structure, tertiary structure. So different forces like this try to hold the structures together. So in lipid bilayer also, some hydrophobic effects can be there. Some dipole-dipole interaction. Like just go through that lecture on self-assembly. All right.
Proteins are more than hydrogen bonding. I don't know if it's correct, right? Like as we go through structures, like the tertiary structures, I think there are more than H bonding that makes them more stable.
Some hydrophobic bonds, hydrophobic interactions also takes place in case of protein. So if you were to talking about tertiary structure like globular structures, so the people have reported that the center of the globules are usually hydrophobic. All the hydrophobic amino acids, they try to go inside, like glycine, alanine. These hydrophobic, they are hydrophobic in nature. They are not having any polar group, so they are protected. So they form the core. Whereas the hydrophilic or the polar amino acids, they form the shell. And that makes the structure much more stable and like makes it insoluble when they are like in an aqueous environment. So yeah, and there can be multiple forces, not only hydrophobic forces, hydrogen bonds can also exist. So multiple type of non-covalent bonds can also uh, together work to create a very high dimensional structure like protein structures. Just go, yeah. So just go through the lecture of self-assembly quickly, and there are many examples of self-assembly and how it is seen in our body has been mentioned. All right, it is based on that lecture only. Similarly, what kind of interactions can play a role for self-assembly of tyrosine fibrils? So tyrosine is a type of a amino acid. All right. So, and it has aromatic rings. So based on this information, can you guess which type of non-covalent interaction can play a role here?
Hydrophobic.
Hydrophobic. Okay. So as I mentioned, it has aromatic rings. Tyrosine, if you see the structure of tyrosine, it is aromatic rings.
Yeah, pi interaction.
Yes, that's
Yeah.
correct. Pi interaction is correct. Here, the delocalized electron clouds are there within the rings. So some type of pi interactions, either in parallel plane like this kind of interactions can take place, and that can cause the assembly. These are dominant forces again. All right. Now these are the images shows three techniques of scaffold fabrication. All right, and you have to label these techniques correctly. Let me zoom in for technique 1. You have to tell me what this technique is called based on this image. So what is happening? Here we have a ceramic suspension. All right. These all techniques are based on ceramic biomaterials. Means you use this scaffold fabrication technique to make a scaffold out of a ceramic material. So you take a ceramic suspension, you incorporate liquid. So for example, H2O2 by stirring. And what happens? You then cause either you keep it in heat or something like that, that can cause H2O2 to evolve oxygen. Okay. And when you dry it and sinter it, you get a porous ceramic structure. So what this technique would be labeled as? Here, the liquid is incorporated like H2O2 to evolve some gas. And when that gas leaves, it leaves behind pores. So this technique would be called as or can be categorized as which technique?
Leaching.
Leaching. Leaching, we add some porogen. All right.
Okay.
Here
So
we
these
are
are not porous accents.
we are not adding any crystal type of porogen type of a thing, means that dissolves out. We are not dissolving it. We are adding a liquid like H2O2, okay, which under a high temperature it will release gas, oxygen. And when that gas is
Yeah,
released,
gas forming. Gas forming.
yes, that's correct. So it's a foaming method or gas forming method. Okay, this is the second one. So this technique, here what we are doing, we are taking a polymer, all right, and we are making a very porous mold out of it. This is the mold, very porous mold. It is then solidified and all. And after which, after solidification of this mold, which is made out of a polymer itself, you coat the mold with your ceramic solution. entire, like completely it is molded, very nicely it is molded. Very nicely it is coated, sorry. Okay. After coating, you do sintering, means you heat it at a very high temperature, like 1300 degrees Celsius. So what heating will do? It will basically burn out this polymer, and your ceramic, it will get cooked. You're cooking the ceramic, right? And when you get the final product, this is the final product, that how it would look like. Okay, so what this technique would be called? This is specific to only bioceramics. Again, usually with polymers, we don't do like this.
Process is clear, but the name is unsure.
Okay, it's fine if you're not getting others. What about others? It's called sponge replica method. We are using a polymer to create a mold that looks like a sponge, which looks like this. If we do close-up imaging, the image, it would look something like this. All right. Then we coat the entire sponge-like structure with our ceramic. Very nicely, you have to coat. You have to make sure that the entire material is well penetrated within the mold. And then once it is done, you take the entire thing and you heat it at a very high temperature. So what it will do, it will burn out this mold, positive mold, and what you will have a negative of your ceramic. And it is, since it is heated at a very high temperature, it will get cooked. All right, like you cook clay pots and all. Similarly, you're cooking that. That is, this method is called sponge replica method. All right. This is another method very commonly used for making ceramic based scaffold. Here, what we are doing, this is your work area. All right, this is your work area. And uh, on top of it, there is a laser. First, a roller will create a thin layer of powder over your work area. Then the laser will come from the top. It will uh, basically sinter, means the particles, they are uh, like powder particles, they are very cooked at a very high temperature. Laser is a very high power laser is used. So selectively, at selective regions, the laser is allowed to fall and it causes sintering of the powder particles. Okay, this is, and then what happens? The next, again, the lower roller will come, and on top of it, again, it will put a powder. So it is a kind of an additive manufacturing technique. Here, structure is getting formed in a layer by layer manner. One layer of powder is deposited, and then top of it, laser is shown such that it sinters the powder at specific locations. Once that layer is done, then again a layer of powder is given and it is repeated until the entire structure is formed. So it is a type of additive manufacturing technique. But what it is called?
This is 3D printing.
No, it is not
No, it's not.
printing.
Okay.
It is called powder laser sintering.
So 3D printing, on the other hand, just like prints it layer by layer and not really using powder or basically sintering support. There is no
Yes.
layer sintering over there. So in the 3D bioprinting, it's just basically layering up different layers of biomaterials, I guess.
Yes. So
So,
when we
but in
talk
some other
about,
hand, it's like getting a mold by like cooking it in between the processes.
yeah. So when we talk about bioprinting, first of all, we are working with some biological component. So we won't be using such high power laser, first of all, because it will harm, right? It will kill the cells, or if you're using some protein growth factors and all, it will get degraded. So we use very gentle conditions, first of all. And 3D power printing is usually done with polymers, another main differentiating factors. You use hydrogels, or you use hydrogel and ceramic composite kind of a thing. And you can either extrude it in form of filaments, you can deposit drop by drop, means very aqueous phases are used. Liquidy aqueous phases are used for bioprinting or 3D bioprinting. Here we are talking about powders, means granules of ceramics. All right, they are like sintered at a very high temperature using laser power, and then it is like means stacked. In that way, it is stacked.
But even in this case, also we're using the bioceramics, right? No.
Yes,
Yeah.
this is a technique used for bioceramics, used for creating scaffold made out of bioceramics.
Okay.
Okay. So I wanted to briefly discuss about 3D bioprinting, as it is the field that I'm working in. Um, Although the lecture slide is there, just briefly discuss. All right. So 3D bioprinting is basically a additive manufacturing technique, as I told you, because material is deposited in a layer by layer fashion. All right. Now we are known of three techniques, three ways where 3D bioprinting can be done. We can extrude, that is called extrusion. We can deposit, where extrusion, where filaments are extruded. All right, filaments. Then drops or inject printing is possible, where drop by drop assembly is there. And there is also light based, where uh, light of very in the nanometer range of visible light, means 400 to 700 nanometer light, which is biocompatible, means cells will not be killed. So in this range, light is used to photo cross-link the polymer. Here, photo cross-linking is done, photo cross-link the polymer in a layer by layer fashion. All right. So these are main three techniques that is being reported in literature and people around the world are working on. All right. So individual, and how would you do 3D bioprinting? So first you have to make a 3D model. All right. You have to first make a 3D model. So if you are working with the clinician, suppose, and that person needs you to make a 3D structure that is going to fit the defect site, then in that case you can use the images from his medical images, it also called, from his MRI scan or CT scan, okay, or ultrasound. You can use those scanned images to reconstruct in digital form. That is called CAD model. You make a CAD model, a digital 3D model. Okay. Then you export this CAD model into the machine, 3D bioprinter machine. The machine can read the CAD model in the format .stl. This format is supported, okay, in a 3D bioprinter machine. The machine, how it prints, basically it will have a robotic arm, okay, a robotic arm that can move in X, Y, and Z direction. So it can move throughout the three dimension. And as it is moving, it's either going to extrude a filament, or it will eject drop, or if it is light based, then here light source is moving. The light, if it is there, this light can move, or light can move, sorry, light can move in XYZ direction, or it is also seen that the stage onto which the structure is going to form, that stage can move in XYZ direction. And the movement, how it is controlled, the machine can convert the STL file into a file called G code. What is G code? G code is nothing but instructions which says how much X to move, like 0.01 centimeter to move. Okay. Then Y 5 centimeter it will move in Y direction. Then Z, suppose you don't want to move in Z, then it will say that Z move 1 centimeter, means 1 centimeter Z will move. In this way, in X and Y coordinate, the code is translated. From STL file, you get a G code where X, Y, Z code. Yes, yes, you have a question.
Yeah. I understood about the it's just like 3D printing, normal 3D printing.
Yeah, that's it. Yeah, you have
So,
seen the 3D printing process. It is just like that. Yeah.
but then I'm very unsure about the light based, because is there a separate substrate to which the light is treated on, or how is it going to be?
Okay. So here for light-based technique, what happens? Very commonly, the light-based, so there are various light-based techniques available. I'm specifically going to focus on SLA, or stereolithography, or DLP, digital light processing based technique, because these are the techniques most widely used right now in literature. So here what happens? Here there is a stage, all right, and you onto the stage you keep a vat or a petri dish containing your polymer, which is a photo cross-linkable polymer. It can only form covalent bonds in presence of light. And in case of DLP, what happens is that the CAD model you load, it gets sliced and creates a G code. The G code gives an instruction of how the layers would look like, each digital layer, how it would look like, means how the robotic movement will be there to create each layer, right? So that information is given through CAD and translated through light. So basically a light-based digital mask gets created. So, sorry.
No, it's the light based digital.
Mask means, let me explain it bit more detail. So this is the CAD, all right? And suppose the CAD was of a cube and G code gets formed. So if you slice this cube, what will happen? You get 2D images, right? Of a square, something like this. Okay, you get 2D images, series of 2D images of a square that are stacked on one another. That is your G code.
So you're basically lighting up so that you're building it from the base layer, but then it happens inside the substrate or the cross-linkable, what is the material? I forgot. The light-induced cross-linkable biomaterial. So basically, it occurs layer by layer inside the substrate in the petri dish itself.
Yes, yes. So the petri dish is there, all right? This is your polymer solution, and the light which is falling from the top is actually first, if it is going to make the first layer, the light is going to fall in a square manner. That is called light digital mask. It's light, it is like forced to create that square. And when it falls, the square structure, when it falls, or the light, when it falls in a square form, the polymer is going to, first layer of the polymer is going to cross-link like a square. Okay. And the cross-link structure starts appearing here on the top stage where the light is there. And then this particular stage will move down a little bit. Okay. And then
So because of the
the
density.
then the next layer based on how the light mask is coming for the next layer, it will accordingly get cross-linked in that geometry, and then it will stick to the this layer. So the structure is forming in an upside down manner. So if this is your top, this is your bottom, the bottom will get created first, and the entire thing, this is actually submerged. This stage is completely submerged into your petri dish, which is containing your polymer solution. All right. And as each layer of the G code gets executed, you are able to see that because of how the light is falling on the polymer solution, it is stacking up on a layer by layer fashion.
So for the initial layer, we adhered to the bottom because yeah, it would be okay.
Yes.
Would the initial layer would it be adhered or like stuck onto the bottom of the
Bottom.
petri dish?
Yes. No. It will get adhered on a stage like this. Stage through which the light is coming. Here it's transparent, so light can come through. All right. And
Okay.
so here, after the printing is done, you will get a petri dish which is still in liquid form. Because here what we are doing, we are also at the same time removing the uncross-linked polymer. We don't want unnecessary cross-linking to happen, right? If the
Yeah.
cross-link like happens within the petri dish, and then the light non-specifically also binds with the surrounding polymer, so you won't get very nice resolution in that case. So that is why it is like removed, and then you can wash it if you want, and then use it for other purposes. Okay, this is just one mechanism that I tried to explain. There are means large amount of videos are there online, in YouTube, basically, that will help you visualize better. I didn't have a video resource with me today, so that's why I couldn't. Maybe next time, next week, I'll show you a couple of videos for 3D printing, like how different type of 3D printing is done. So that will help you visualize better the process. All right. Next week, I'll show you guys. So yeah, this is it I had for today. And please go through the lectures of this week and then start attempting the assignment. If you have any queries, please put your queries in the discussion forum. I'll try my best to answer them. Also, if it is still not answered, you can ask me in the next week. If there are any queries from any one of you, yeah.
Okay, I don't think we can ask questions over here regarding our course, can we?
Uh, I'll try my best. If I'm not able to get it, then yeah. What is your query anyway?
No, the thing is, no, it's a personal prayer. It's not like a.
Okay. Okay.
No, I just know that the meeting is recorded for the later on purposes. So,
Okay, fine.
yeah.
So if you would like, you can mail NPTEL directly, or you may directly mail the faculty if you want it to be private.
Okay. It's not very bad.
It's fine. Any query related to what I have discussed today? If you have query based on that, I'll be happy to take up.
The one last that I had, like while we were explaining, was about how the printed material would be staying stable. Uh-huh. So compared to the other techniques, I think those materials are like fastened onto a stage whereby it's printed. But on the other hand, the light infused method, they're like in the floating substratum, right? In the cross-linked polymer liquid phase. And then later on, they're converted into the solid phase by lighting mixing. So wouldn't it float off was the thing that first ran up to my head.
So it means you're saying it will
Move away, and which gives us a bad resolution.
So it can happen. You're not wrong. It can happen. One has to optimize like the geometry of the Petri dish, how big you want it, then the volume of the cross-linking solution. So if the volume, you have to use only that much volume that is required. If you use more than the problem that you're saying, that can happen. So the machines that comes here for this application, they're very smart, all right? So you will load the CAD model and it will tell you how much volume of ink to use. And you have to like only load that much of volume, means it will tell you this is the entire 3D structure, so it will calculate how much volume to use. So if you do a couple of times, then yeah, that problem can be solved, but it can happen. It is not unobvious for it to happen. Any other queries? Like, was I able to answer it?
Yeah, I mean, yeah.
Yeah. Does anyone else have any other queries? So you guys are done with week 1 and week 2 assignments. How did you guys perform?
And the thing is, I missed.
You missed? You didn't do the
I,
assignment?
no, I couldn't.
No problem. But try to attempt it. Otherwise, like
But
when you're
then I saw the assignment. You had to do 6 out of 8. The average is taken. So I think I have 6 more, which I have to do. Then I will be fine, I guess. That is one
yeah,
query that I had, which I said I'll later on.
yeah. So yeah, that is the requirement actually. You have to score above 50% in assignments as well. Apart from the exam, you have to also score good in the assignments to get a certificate.
So I think it would be fine if I continue over with the third week onwards,
Yeah, yeah, yes.
right?
Mm.
Because I'll have 6 assignments, right? I just need to do.
Yeah. Okay. If there are no further queries, then thank you all for joining and we'll meet, all right, in the next week. We'll be discuss week 4 content. But if you have any queries regarding these 3 weeks, just let me know. All right. Okay. Guys can now leave the meeting.